We got a new term we're going to be using and a lot with our distance formula. It's called locus. And when I refer to the word locus, I mean the set of points that fit a given condition. So when we refer to a set of points, usually we make those set of points, as an equation of a line or a parabola or something like that. So usually we have some equation that refers to a bunch of points. And don't confuse this with locus that ends with a T, which is essentially a grasshopper, right? So locus without the T is a set of points that fits a condition, where locust is a grasshopper. So just locus, no T's in this guy. And how we're going to use that is, first of all, like this. We're going to find the locus of points that are as far away from the point 2, 4 as they are from the point -1, 5. So I got a little picture here. We got the point -1, 5, and we got the point 2, 4. And I want to come up with all of the points that are equidistant from those 2 points. So for example, like this point that I drew here, these red lines should be equidistant, but they're really not. So this picture isn't that great. But, like this point, about like right here, somewhere in there. And, this point up here is pretty close to being the same distance. And like this point. So if you notice, as I keep making these points, eventually, it almost makes like a straight line in this case. So there's really a line that's going through a bunch of points, and at any point on that line, it's going to be equidistant from those 2 points. Okay, so they have this little picture here for you. Really, it's not drawn to scale because these red dashes should be the same. But we're saying that, the distance of this one, distance 1 we'll call it, and the distance of this one, distance 2, should be the same. I'm going to use a different color. Let's go distance 2. They have to be equal. So really, we want distance 1 to equal distance 2. Well, how could I write D1 out? How could I write the distance for, this red dashed line right here? How could I do that? Well, let's use our distance formula. So D1, to find that distance, we would take the square root of, how far apart are the x's? Well, this one we don't know, so we're just calling it x. And this one's -1, so x minus -1. And we square that. And plus, we don't know what this is, so we call it y. And y minus 5 to figure out how far apart they are and square it. So there's distance 1. And then I would do the same thing for distance 2. The square root of, that same point, that xy point, we don't know what the x is, so we use x. And to figure out how far away is from 2, we'd say x minus 2 squared. And we could say plus y minus 4 squared, right? Because we don't know the y. Figure out how far it is away from 4. And we said we want these guys equal, so we're going to set these two guys equal. So D1 is really what? The square root of x plus 1 squared plus y minus 5 squared. And D2 is really x minus 2 squared plus y minus 4 squared. And we want to simplify this down in order to write an equation for a line. So basically, my goal is to solve for y in this case. Well, let's get rid of these square root bars. How would I do that? Oh yeah, square both sides. So that would cancel this square root, cancel the square root, and I'd be left with x plus 1 squared plus y minus 5 squared equals x minus 2 squared plus y minus 4 squared. Okay, and I can't square root to get rid of these squares because of the plus signs in between, so that would not work. I couldn't square root both sides here. But what I could do is expand both of these out. So that's what I'm going to do. X plus 1 squared. Well, remember that's really, x plus 1 times x plus 1. It's the factored form of a perfect square trinomial. So that's going to give us x squared plus 2x, because it's really 1x and another 1x, and then plus 1, 1 times 1. So the better you are with your factored form with perfect square trinomials, the quicker this part will be. So when I do y minus 5 squared, that's going to be y squared. And we'll have a -5y and another -5y for -10y. And -5 times -5 is positive 25. So there's that part expanded. Oh, I'm going to run out of room here. And then I'll do the same thing over here. So I'd have x squared minus 4x plus 4, and then plus y squared minus 8y plus 16. So lots of stuff. And now let's start looking at it. You know, if on both sides of the equal sign I have an x squared and an x squared, so those cancel each other, right? I could subtract an x squared from both sides. Same thing with my y squareds. They cancel. All right, now let's start moving our x's and y's around. Well, I got a 2x and a negative 4x. I'm going to add a 4x to bring it over here. So now I'll have a 6x on the left side of the equal sign. Might bring my equal sign down. Okay. Let's deal with my y's. I'm going to add a 10y over to this side. Add a 10y. So that's gone. And over here, negative 8y plus 10y gives me 2y. Okay, done with that. And then 4 and 16 gives me really plus 20. And 1 and 25 really give me plus 26. So if I subtract 20 from both sides, this is gone. And then I have plus 6 over here. So really I have 6x plus 6 equals 2y. And then to solve for y, we divide by 2. So y would equal 3x plus 3. So there's the set of points that are the same distance away from 2, 4, and negative 1, 5. And if I graph that, that would be a y-intercept of 3. So that would be right here. And then it goes up 3 and right 1, because the slope of 3. And then down 3 and left 1 as well. So really that line right there. So if I picked any point on that line, it would be equidistant from the 2 points. So there we go. It takes a little bit of work, doesn't it? Okay, and the more you do, the quicker you go about this. So for example, when I set these two guys equal, I basically just don't even worry about the radical signs right away, and I just start expanding them out. I don't even really worry about the x squareds and the y squareds because I know they're going to cancel, things like that. So you get used to how that can simplify down when you find the locus of points. Okay, and the same can be done from a point and a line. Okay, the only difference here is that with the line, we want to consider the distance perpendicular from the locus of points to the line. That's kind of the main key here, and that's why I drew this in. We got this line. We're going to consider the line that's perpendicular. So if I looked at another point for the locus of points, let's say like, up here, let's say that was xy. So if that was a certain distance away, we would want that same distance to be perpendicular. Okay, so this is going to have a little bit of a curve to it if we think about it. So let's kind of deal with the same way. Let's start it the same way here. So I want distance 1 to equal distance 2. Well, distance 1, so distance 1, let's write an equation for that. So the square root of, so from, x to 3, so x minus 3 squared, plus, and from y to 6, so y minus 6 squared. So there's distance 1, so I'm going to fill that in right away. The square root of x minus 3 squared plus y minus 6 squared. Okay, and we're going to end up setting that equal to distance 2. So let's think about this now. So the x's, well, if we consider the line perpendicular, the x's are going to be the same value, right? Because it's always going to be x and then 2. And this point, right here would be x and then 2. Because the x's would actually match each other. So really we're going, x minus x squared, which is really 0 squared. So that's 0. So I don't even need to consider that case. And then here we know that it's always going to be y minus 2, right? Because all of these points are going to have a y value of 2. And we square that as well. So when I bring this down, I have the square root of, well, I don't need to consider that 0 squared. So it's really just y minus 2 squared. And then we do the same thing previously. We square both sides, so the roots cancel, and then I expand out all my binomials, my instead of x squared minus 6x plus 9 plus y squared minus 12x plus 36 equals y squared minus 4y plus 4. And then you start going through your algebra, right? So really, we do the exact same thing. We want to solve for y. It's kind of our goal, so we can get an equation. So these y squareds cancel. And Oh, I do this all the time. This shouldn't be negative 12x. This should be negative 12y. Something I like to do is to always do x's. I don't get it. So I'm going to get my y's to the right side of the equal sign. So I'm going to bring my equal sign down. So I'm going to add this 12y over right away. Add 12y. So that's gone. This would be 8y. And then I'm also going to subtract this 4. So I'm just going to subtract it from the 36. That's fine. So this really becomes 32. And now I can simplify things on the left side of the equal sign. So I got x squared minus 6x, and 9 and 32 make plus 41. And then we get the y by itself, so we divide by 8 on both sides. And I'm going to flip-flop these. So y equals, well, x squared over 8 are really 1/8 x squared minus 6/8, which is really 3/4 x, and then plus 41 over 8. I'm just going to leave as 41 over 8. So there is my equation. There's the locus of points. And if I were to graph that on my calculator, we would see that it would make a parabola. Okay, and then this can also be applied to story problems. And it gets kind of tricky how you set these up because they get set up differently depending on what you're given. So here's an example. It says Josh is riding his mountain bike when he realizes he needs to get home quickly for dinner. He's 2 miles from the road, and home is 3 miles down that road. He can ride 9 miles per hour through the field and 22 miles per hour on the road. How can he get home most quickly? And then how long will it take? Oh boy. So let's think about this. The easiest way to do this is to draw a picture. So for example, Josh is here, okay, and there's a road going home that is 3 miles long, right? So this road is 3 miles, and he's 2 miles from that road. And so we want to imagine him, biking at an angle for 9 miles per hour, and then biking the rest of the way on the road at 22 miles per hour. So this way he's going 9 miles per hour, and the rest of the way 22 miles per hour. And we want to figure out the time. We want to figure out how long this is going to take. So this is kind of important, like how far down the road he should shoot for, kind of like what angle he's going to be riding at to get this route to be the fastest. Right? Because obviously he wants to ride more on the road. So let's consider it. So I got a little nicer picture right here. And basically what is happening is he's traveling a certain distance right here. And he's traveling another distance right here to get home. And you might be thinking, well, we've been using the distance formula, so would we use that? Well, let's just be careful. We have a rate now, right? So when we have distances and rates and we're looking for times, what do we want to use? Yeah, we want to use the dirt formula instead. Right? We got a rate now, so let's go back and think about how that rate can be applied. Well, let's just kind of write things down. So I got this distance 1 over here that he's going to travel, and then I got this distance 2 down here that he's going to travel. So I'm just going to write equations for both those. Well, what's the rate for distance 1? How fast can he bike, right? 9 miles per hour going this way. So there's the rate. And we don't know the t, so I'm going to leave it as t for now. And how about on the other side, distance 2? Well, the rate t can go here is now 22 miles per hour. Okay, and t for time for that trip. All right. Well, I don't know the time. That's what I'm trying to find. Could I write something for the distance here? Well, yeah, now that's where the distance formula comes into play. That's right, the distance, using the distance formula for d1. So d1 is going to really be the square root of what? Remember, it's like the distance horizontally. You take like x2 minus x1 squared. Well, we already found what that is, that x2 minus x1. It's really just x right here, right? So he's traveling x distance horizontally, so x squared, plus 2 miles vertically, so 2 squared. That's our distance formula. And that's going to equal 9t. And then I can do the same thing over here. Except I know that he's traveling what? Well, if he's already gone x amount of miles horizontally, all he has left is this piece right here, which is what? 3 minus x. So that's what I want to use for his distance. So he's really 3 minus x, and that is equaling 22t. So that's where it gets a little bit confusing. Okay, well, what's similar about these two guys? Are these t's really the same thing? No, they're different times. Okay, I might call this guy T1 and this guy T2 just to confuse us because they're not the same thing. But what is the same about these equations? Yeah, the x is the same. I could solve for x and substitute in the other equation, but what would be helpful here? Well, the total trip is going to be the time it takes for the first part of it, when he can go 9 miles per hour, plus the time it'll take for the second part of it. That'll equal, the total time that it's going to take. Well, if I solve these both for their t's, I could plug them in for T1 and for T2, and then see how that would help me. So in this first case, I could divide by 9 to get rid of that 9 there. So T equals the square root of x squared plus 4 over 9. And T2, I could just divide by 22. So I'd have plus 3 minus x over 22, and that equals, and so this is equaling the total time for the trip. So let's bring that down here. So the time it takes for the first trip is x squared plus 4, all over 9. The time it takes for the second trip is 3 minus x over 22, and that would equal the total time, which in this case, I guess we could represent it with y. We could say y is the total time that it's going to take. So this is really T1, and this is really T2. And what we're trying to find is the minimum y value, right? The minimum time that it would take. So if I graph this, you think about a parabola, there's a minimum on a parabola, correct? And the fact that I have an x squared, I should get a parabola out of this if I would graph this on my calculator. So let's try that. So I go in, I graph it, square root of x squared plus 4 divided by 9 plus, make sure that I put parentheses over my 3 minus x because there's two terms, divided by 22. And I went ahead and graphed it. And I zoomed mine in a little bit. I started with zoom standard, then I zoomed mine in so I could look at it. And it might even help to trace just to kind of look and see what we mean by this stuff. So this is your total time of the trip. This would be the distance of that x, how far from his initial spot in that horizontal direction is being taken up here. So, and we want to find the minimum time. Well, we have a minimum calculation that we can use. So we can go to second calc and minimum. We've done this for our vertex of our quadratic. Well, I'm going to start it when x is 0 because it's hard to see where my minimum is here. And then I got to go right bound, so I'm going to go right of the lowest point. It's kind of hard to tell where that is, so I'm going to go way right just to be safe. Looks like it's starting to increase up here, so I'm going to go over here. And then take a guess, enter. And there we go. So there's my x value for the minimum time. And here's my minimum time. So I might write both these down. So the x is, it was about 0.8966, I believe. And the time, the total time was 0.33, about 0.339. And the question was asking for how long it will take. Well, the time, 0.339, and he'd basically travel, about 0.9 miles down the road initially. I could figure it out in minutes, but that's totally fine for hours. So it gets kind of tricky. It takes a little bit of time, but you have to really think through it. But I could have done this without drawing a picture.